All right, guys, this is 7:03, the video for work. So we said earlier in our other videos that work is capital W, and it is equal to force times distance. We need to add a little bit of detail here. I'm going to do some adjusting here. It's a little bright. Okay. So it's not just any old force. So if I take a box and I push it, let's do a couple of free body diagrams. All right, let's do two boxes. And let's say I've got, of course I have my, we're on frictionless. So I've got my normal and my gravity. Those are equaling out. Let's say for one, I push the box perfectly horizontal, and for the other, I push the box at an angle. So we've got the applied force. So I have an applied force here. I have an applied force here. And my motion, so I'll do my motion vector, is here. So we define work as force that moves an object over a distance. And in this case, if I look at this example, this force, let's say I go for a motion of 2 meters. This force times 2 meters would give me my work. But if you look at this example, oh, and you know what I didn't do? Shame on me, coordinate system. Let's get a coordinate system there. The components of this applied force are not 100% along my motion pathway. My motion is here, my force is here. So what we see is when I split this out, I have FAY and FAX. So that's a Y, doesn't look like a Y. It is this component of my force that's causing the motion. Here. That showed up very well. And so I have to be careful. A better way to write this as the definition for work is the parallel force, or I should say force that is parallel to my motion multiplied by the distance. I like to write this as work equals force parallel times d, where the two symbols indicate parallel. In textbooks, you'll see it written as force cosine theta times the distance, because if this is my angle here, then if I multiply that by cosine of theta, that would give me the correct component of my force. There's an aspect to this I don't like, and I will explain that to you in a bit here. I think the easiest thing with these, we're going to have a lot of really small equations that are going to just kind of pop up, and I think the easiest way to tackle them is to look at examples. So I start off, I have an intern pushes a 72 kilogram patient on a 15 kilogram gurney, producing an acceleration of 0.6 meters per second in a patient gurney earth system. How much work does the intern do by pushing the patient and gurney through a distance of 2.5 meters? Assume that the gurney moves without friction. So we're frictionless, and we've defined our system as the patient, gurney, and the earth. So if I wanted to, I could do a free body diagram. I don't necessarily have to. I don't necessarily have to for this one. So we know that they're asking for how much work does the intern do. So we know that work, let's go green, is my parallel force times my distance. I have a distance of 2.5, but they don't give me a force. They do give me an acceleration of 0.6 meters per second squared, and they give me masses. So I have masses. Now, they have the patient in the gurney, but it says my system is going to be the patient gurney earth. So that means I'm going to have to add these masses up. I'm going to do 72 plus 15 is going to give me 87 kilograms. Well, I don't have this, but I do know that force is equal to mass times acceleration. So I could rewrite this expression to be work equals mass times acceleration times distance. And you can see here what I've done is I've done an expansion. So I've taken a formula and embedded a sub-formula inside of it. We're going to begin to see this more and more and more. When I multiply this out, I get 87 times 0.6 times 2.5, and that gives me a value of 130. I'm going to write it up here. What's my unit? Force is newtons and distance is meters. So I could say this is 130.5 Newton meters. But usually when you're talking about work, you'll see work as Newton meters. But how else could I write this? Well, remember, force is mass times acceleration. So this is kilograms. This is meters per second squared, is acceleration. So the other way to write this is kilograms times meters over second squared, and I have another times meter here. So a Newton is a kilogram meter per second squared, and that's a meter. And that gives me a net unit of kilogram meter squared second squared. Well, scientists take these derived units and they rename them. And what they did was they renamed kilogram meter squared second squared as a joule. So our equivalencies, a joule is the same as a kilogram meters per second squared, is the same as a Newton meter. Those are all the same thing, and you should know that. Okay, I want to jump down to sample number 3, so I'm going to slide my paper here, where we have a block is pushed at constant speed. What is the work done by the following forces, and what is the sign? And we want to talk about work and signs. We talked about that a little bit previously. So this time I am going to do a free body diagram, and we have constant speed. And I'm going to go with blue here. So I've got my normal force. I've got my weight vector. I have my applied force. And I have my force due to friction. And they want to know what is the work done and what is the sign. So in the previous videos, we talked about the fact that if the force and the motion are in the same direction, I have positive work. If the force and the motion are in the opposite directions, I have negative work. Well, let's assume my motion is here. Doesn't look very green, but it is. All right. So we define work as forces that are parallel to motion. So what do we know right away about gravity and about the normal force? Are they doing any work at all? These are perpendicular. So these are perpendicular to my motion. So these are doing zero work. And if I look at my applied force is going in the same direction as my motion. So this is going to do positive work. Here I have friction, and it's going in the opposite direction of motion. So this is going to do negative work. Well, what about my net force? Is my net force doing any work? What happens if I add all these vectors up, guys? My net force is 0. So that means my net work is equal to 0. Even though I'm moving, yeah. So you have to be careful how you look at these problems. You need to say, okay, what do I have going on? In this case, the applied force is doing work and the friction force is doing negative work, but they're doing it because they're in opposite directions and they're equal in value. They're going to cancel out and my net work is going to be 0. All right, let's look at one more sample problem. Let's go to this number 2. In a gravity escape system, an enclosed lifeboat on a large ship is deployed by letting it slide down a ramp and then continuing in free fall to the water below. Suppose a 4,900 kilogram lifeboat slides a distance of 5 meters on a ramp that makes an angle of 30 degrees with the vertical. In a boat or system, how much work does gravity do on the boat? One of the things I want to point out right away is that this says 30 degrees with the vertical. Now, everything we have had has been an angle with the horizontal. So why did they change it? All right, let's look at this. Let's do a free body diagram here. So here's my ramp. Here's my boat. We're assuming frictionless. I don't know if the problem says that, but we're going to assume frictionless. And so I have my weight vector. Here's FW. And we're going to go ahead and tilt our coordinate system. So I have FWY and I have FWX. Now, everything we've been given has been here, and we know that this theta is equal to theta here. What they're saying now is they're giving us theta 1, and that's going to be equal to theta 1 down here. So they said 30 degrees, which I can tell right away, this isn't drawn to scale. I should have made this a lot steeper. That's obviously not a 30-degree angle. They're talking about 30 degrees with the vertical. So they're saying we have 30 degrees here instead of 30 degrees here. Well, why would they do that? Why would they not give us the horizontal? Well, look what happens. If we're talking about our value here, which is going to be 60. So this would be 60, and this one's going to be 30. The formula that's written in the textbooks all the time is work equals F cosine theta. If they gave me the angle with the horizontal, is the horizontal component. This is the part that's doing the work. So this is the part, my motion is here. I've got my motion vector. So there's my motion vector. So that means that this component of gravity is doing the work. And usually I get a horizontal angle. If I do my trig function to get this, and I use this angle, is it still a cosine function? It's not. If I used these angles, I would have to use sine to get this component. And this is not consistent with the formula they always give you. That's why I don't like this formula. I would rather write it as F parallel, whoops, got my distance up there, times my distance. And that way I don't have to worry about, do I have the right trig function or not? But in this case, they do give us the vertical, and so that gives me my angle here, and so I can use the cosine function. And so if I get my force times cosine of 30, and my distance is 5 meters, that's going to give me my work done. Well, how do I find this force? Well, hopefully you know that if you want your weight vector, the force of that, that's equal to mass times gravity. So I'm going to now rewrite this equation as, let's make gravity 10. So this is going to be mass times gravity. So I have 4,900 times 10 cosine 30 times 5. And when I multiply that out, I get 212,176 Newton meters. What are our takeaways? We talked about the fact that you have to consider not just the force, but make sure you have the right component of the force, because it's not always the entire force that causes the motion. It's the force that is parallel to the motion. We talked about the unit. It's a kilogram meter square per second square, which is the same as a Newton meter, which is the same as a joule. We talked about the fact you have to be careful at looking at whether you have positive work, negative work, or zero work because you're perpendicular. All right, that is everything we need to deal with work. We'll work some more sample problems in class, and we're going to start talking energy in the next video. Thanks for watching.